Greetings to all of you. I am a Professor M.I. Vyas, Associate Professor, Government Engineering College, Modasa. Friends, we have already started to learn properties of gas. In the properties of gas, we have seen last time what is vapor and gas. Vapor is the intermediate state between liquid and gas. Gas is the matter which follows the gas laws, where vapor does not follow the gas law. Then we studied about the Boyle's law, Charles' law, and combined gas law. Then we have also seen the specific heat. In the specific heat, we have learned that heat is the path dependent. So we must specify the process, the path through which it is going on. So from state 1 to state 2. Two useful processes are there, constant pressure and constant volume. So we will consider the specific heat at constant pressure and at the constant volume, that is depend. For solids and liquids, we can neglect this pressure change, and the specific heat capacity that we measure for them is essentially one where the pressure on the body is unaltered. We call this specific heat capacity, that is at constant pressure, Cp. For gases, however, it is necessary to specify the conditions under which the change of temperature takes place. So, in solid and liquid, generally there is no change, while in gas, there is the change because the change of temperature takes place. Since a change of temperature will always produce large changes in pressure and volume, the change in temperature also produces change in pressure and volume always. The specific heat capacity at a constant volume, which is known as Cv, is defined as the quantity of heat required to raise the temperature of 1 kg of gas by 1 Kelvin if the volume of the gas remains constant. The specific heat capacity at constant pressure, Cp, is defined as the quantity of heat required to raise the temperature of 1 kg of gas by 1 Kelvin if the pressure of the gas remains constant. So far when we are talking the specific heat for the gas, we have two specific heat. One is at the constant volume, Cv, another is the constant pressure, Cp. While there is a heat required, or the amount of heat which we supply during that volume of the gas remains constant, that is specific heat, and when the pressure remains constant, it is specific heat at pressure Cp. The early one is Cv, then at the pressure it is Cp. The specific heat capacity at constant pressure Cp is always greater than the constant volume Cv, since if the volume of the gas increases, work must be done by the gas to push back the surroundings. So, our interest is to find out some relationship between Cp and Cv. In order to achieve this, last time we have seen the Avogadro hypothesis. We have also seen the gas constants, universal gas constant, specific gas constant. So now, today we are interested to establish the relationship between Cp and Cv. So let us see how this relationship we establish. Let us say the initial temperature T1, final temperature T2, right? Similarly, you can write down initial volume V1, final volume V2. Temperature is in Kelvin, volume is in meter cube. Let us say Cp and Cv are the specific heat, One is at constant pressure, another is at constant volume. That is in kilojoule per kg Kelvin. Kilojoule per kg Kelvin. R is the characteristics gas constant. R is the characteristic gas constant. That is also in kilojoule per kg Kelvin. P is the pressure of gas in kilopascal, or you can say, if we convert the Pascal into Newton per meter square, so kilopascal instead that kilo Newton per meter square. M is the mass of gas, that is in kg. Now consider that m kg of mass. Let us say m kg of mass of a gas heated at a constant volume from temperature. So let us see, this is one system. Inside there is a m kg of gas. Inside there is a m kg of gas. We are supplying the heat. We are supplying the heat, and as a result gas is heated from temperature T1 to T2. The process is carried out at a constant volume process. The process is carried out constant volume. The entire heating is carried out at constant volume. temperature get changed from T1 to T2. There is a m kg of mass inside these vessels. So we are supplying the heat which we have supplied is at constant volume. So QV, because that volume remains constant, it is mass into specific heat as it is constant volume. We are supplying the heat at constant volume, so we are using CV. And there is a change in temperature. That is temperature increase from T1 to T2. Temperature increase from T1 to T2. So change in temperature is T2 minus T1. Change in temperature is T2 minus T1. Now, when the heat is supplied at a constant volume, no external work is done. When the heat is supplied at a constant volume, so there is no external work is done. So what happened? Whatever the heat we are supplying, all the heat energy is utilized for the change in the internal energy of the gas. As there is no external work done, all the heat energy utilized in internal energy, all energy utilized in internal energy. So as a result, there is a change in internal energy. There is a change in internal energy, and this change in internal energy, you can say it is delta U. The change in internal energy is delta U. So that comes M into CV T2 minus T1. Right? This is what the total heat we supply utilize in change of internal energy. Correct? Now we'll take another case. When it is heated at constant pressure, when the gas is heated at constant so amount of heat supplied Q at constant pressure is equal to mass into, now you take, when it is a constant pressure, we are using CP. we are using Cp into change in temperature T2 minus T1. Now, when the gas is heated at constant pressure, the amount of heat which we supplied, is utilized 1 for increasing the internal energy, increasing internal energy, and second, it is utilized to overcome the external resistance, This you can call it is a work done. So at a constant pressure, gas is heated, the amount of heat supplied is equal to M into Cp into T2 minus T1. The heat which we are supplying utilized for the two purposes. In two aspects the heat goes. One, for increasing the internal energy. Second, to overcome the external resistance, which is called work done. So, therefore, increase in internal energy, whatever the rise in internal energy is equal to M Cv T2 minus T1, and the work done or whatever the heat is utilized here, whatever the amount of heat utilized here to overcome this resistance, that is work done, is equal to P into V2 minus V1. Pressure remains constant, so P into change in the volume gives you the work done. Change in the volume is V2 minus V1. But the amount of heat supplied is what? Qp is equal to M Cp T2 minus T1. This Qp is utilizing over here. So you can write down, therefore you can write down Qp is equal to M into Cv into T2 minus T1 plus P into V2 minus V1. As in our case, in constant pressure, it is given that Qp is equal to M into Cp T2 minus T1 is equal to M into Cv T2 minus T1 plus P V2 minus V1. Now, see, this is the relationship which on the amount of heat supplied at a constant pressure, that amount of heat is utilized one part one part that to change in the energy. This part is change in the internal energy, and this is to overcome the work resistance. Now, consider that characteristic gas equations for m kg of gas at the beginning and at the end of the constant pressure heating. For, you can write down, for m kg of mass of the gas, refer the characteristics gas equation, characteristic gas equations at the beginning it is P into V1 is equal to MR into T1, and at the end of this constant pressure heating, it is P into Vt is equal to MR into T2. Therefore, you can certainly write PV2 minus PV1 is equal to MR T2 minus T1, MR T2 minus T1. So, one is these equations and another is this equation. Let us say this is equation A and this is equation B. So from equation A and B, equation A and B, we can get what is MCP T2 minus T1 is equal to MCV T2 minus T1 plus M into R T2 minus T1. What we did, this portion of equation A, P into V2 minus V1, that we put this value MR into T2 minus T1, MR into T2 minus T1. If you remove the common terms, M here, M here, M here, T2 minus T1, T2 minus T1 and T2 minus T1. What is left out? On this part Cp, on right hand side Cv plus R. So you can write down that Cp is equal to Cv plus R, hence Cp minus Cv is equal to R. This is the first relationship between Cp and Cv that we have established. What we have established? Cp minus Cv is equal to R. and this equation is known as Mayer's equation. This equation is known as Mayer's equation. This equation is known as Mayer's equations. So one relationship is over. Let us move to the next part of this relationship point. See, we have what established Cp minus Cv is equal to R, dividing above equation by Cv on both the side. Both the side divide this by Cv. Cp upon Cv minus this goes, so 1 is equal to R upon Cv is equal to R upon Cv. C. We here define Cp by Cv is equal to gamma. If we define the Cp by Cv is equal to gamma, then gamma minus 1 is equal to R by Cv. Putting this Cp minus Cv in gamma over here, gamma minus 1 is equal to R by Cv. Now Cp by Cv is equal to gamma. So Cp is equal to gamma into Cv. Cp is equal to gamma into Cv. And from there you can write that Cp is equal to R into gamma upon gamma minus 1. Cp is equal to gamma into Cv. So you can put that instead of Cv, you can put Cp upon gamma. Cp upon gamma. If you put here, this Cv is equal to Cp upon gamma. So from there Cp goes this side, gamma goes on numerators, and gamma minus 1 is denominator. By putting this value, simplifying this, you will get Cp is equal to R into gamma upon gamma minus 1. Cp and Cv. And now we are interested to move for some non-flow processes. We are interested to move from this use of this non-flow processes. And this you can have take that relationship between Cp and Cv we have established, we are interested to move the non-flow processes of this gas. So there are some processes on which the gas has to undergo, and that two kind of processes, one is the flow process, another is the non-flow process. Flow process is one in which the matter of the substance enters the system and leaves it after the work interactions. In flow process, mass interaction takes place across the boundary of the open system. So in a flow process, mass enters, some kind of process goes on, the work interactions, and then it leaves the systems. Second is the non-flow processes. The non-flow processes is one in which there is no mass interaction across the boundary of the system during the process. There are different kind of non-flow processes. One is the constant volume process, another is the constant pressure, constant temperature process, adiabatic process, and so on. We will study all these processes one by one in detail. First, let us say the constant volume process. First, we will see the constant volume process. See, what is in constant volume process? Whenever the process goes on, the volume remains constant. The volume remains constant. Friends, this constant volume pressure, the name of this process constant volume, we can also speak that it is isochoric process. It is isochoric process. So you can speak constant volume as well as one can speak isochoric process. So, or also in other terms, it is isometric process. Isometric process. Why it is called like this? Because the term iso, is used to designate that the process remains constant. Iso is the term used to define the process for which the particular property remains constant. During the process, the property remains constant. Which property remains constant? The volume is going to be a constant. So it is isochoric or isometric process. Here the gas is heated in a fixed enclosed space. When it is constant volume pressure, gas is heated in closed vessel. It is heated in closed vessels, so the volume remains constant. The heating will be when it is heated, when the gas is heated as the constant volume is there is a rise in pressure. When the gas is heated, there is a rise in pressure, or pressure increases. Pressure increases. No change in volume, so no external work done. no change in volume, so it is no work done. No work done. Friends, in this chapter in the properties of gas, whenever we are taking these non-flow processes, our aim is to find out, that is, one thing is what is the relationship between pressure, volume and temperature. Second, our focus is work done during the process. Our third objective is to see what is change in internal energy. The fourth one is to find out how much heat transferred takes place. How much heat transferred takes place, and also to see the change in enthalpy. The change in enthalpy. The change in enthalpy. And we will see all the process on PV diagram. We will see the process on PV diagram. So let us say the first process, that constant volume process. We are interested. First, let us see the process on PV plane. So the constant volume process is like this. It started from point 1, it ends at point 2. Throughout that process, volume remains constant. V1 is equal to V2. As we stated, the heat is utilized to raise the temperature. So the initial temperature is, to raise that pressure, initial pressure is P1. And at the end, pressure is P2. So as the P2 is greater than P1, T2 must be greater than T1. T2 must be greater than T1. This is the case applicable when this kind of constant volume process happen. Now, first is relationship between P, V and T. We know that for point 1 and 2, you can write that P1 V1 upon T1 is equal to P2 into V2 upon T2. You are knowing that here V1 is equal to V2. So V1, V2 cancelled out. The relationship you will establish, that is P1 upon T1 is equal to P2 upon T2. The relationship is established is P1 upon T1, P2 upon T2. Next, the work done during the process. The work done during the process. Next is the work done. Work done you can define P into dV. P into dV. For a small change of a volume, you can write P into dV. When there is the whole entire process from point 1 to point 2, the total work done total work done, you can write integral P dV running from V1 to V2. Running from V1 to V2. But volume remains constant. This gives you the 0. This gives you the 0. So work done during the process is remain 0. Work done during the process remain the 0. Now next our interest is that the change in internal energy. The change in internal energy for constant volume process. We are interested next. Our focus is on change in internal energy. Change in internal energy. When the volume remains constant, change in internal energy, that you can write du is equal to mCv T2 minus T1. mCv T2 minus T1. For unit mass of gas, m becomes 1, so du is equal to Cv T2 minus T1. Next is the heat transfer. How much amount of heat transfer takes place? Heat transfer. Heat transferred. So you have with you the delta Q is equal to delta W plus du. This is according to the first law of thermodynamics. This is according to the first law of thermodynamics. Now, so whatever the heat change takes place, some it is with the work done and some in the change in internal energy. But here the work done is 0, so del Q is equal to du. So the heat transfer is equal to m into Cv T2 minus T1. m into Cv T2 minus T1. And last, we can see that for constant volume process, change in enthalpy. For constant volume process, change in enthalpy, you are very well known. The enthalpy is U plus PV. So if for point 1, you can write that H1 is equal to U1 plus P1 into V1. At the end of the process, point 2, it is H2 is equal to U2 plus P2 into V2. Change in enthalpy, you can write it is delta H. The change in enthalpy is what? Delta H. So what is delta H is equal to H2 minus H1. It is U2 minus U1 plus into bracket P2 V2 minus P1 V1. If we H2 minus H1, U2 minus U1, P2 V2 minus P1 V1. So change in internal energy is nothing but m into Cv T2 minus T1. We have defined that change in internal energy du is equal to mCv T2 minus T1. So mCv T2 minus T1 and P2V2 minus P1V1. You can write that m into R T2 minus T1, M into R, T2 minus T1, because that relationship we have with us, that P2V2 is equal to MRT2. You can take P2V2 is equal to MRT2, P1V1 is equal to MRT1. So MRT2 minus T1. Right? You have also Cp minus Cv is equal to R. You have with that Cp minus Cv is equal to R. So you can write that delta H, change in that energy, is change in enthalpy, that is M is equal to M into Cv, T2 minus T1 plus M Cp minus Cv. We have put these are Cp minus Cv here. So Cp minus Cv, T2 minus T1, T2 minus T1. You can open this MCP T2 minus T1, MCV T2 minus T1, it is minus MCV T2 minus T1. So is equal to MCV T2 minus T1 plus M into Cp T2 minus T1 minus MCV T2 minus T1. So MCV T2 minus T1 and M minus MCV T2 minus T1 cancelled out. So change in enthalpy delta H is equal to MCP T2 minus T1, MCP T2 minus T1. So friends, today we have seen that the specific heat, the relationship between the specific heat and the non-flow process where the mass does not cross, the matter does not cross the boundary. And in this non-flow process, we have seen the constant volume process. We have seen that in the context of the different aspects, the work done, the change in enthalpy, the change in internal energy, heat transfer, and the relationship of P, V, and T. You go through any good book and do some exercise on this constant volume process. Next time we will take the small exercise on this constant volume process and then also the other non-flow processes. Till then, a very happy time and all the best from all of us here. Thank you.